Hey y'all, in today's video we're going to take a look at how to determine and justify the validity of a proposed reaction mechanism. When we talk about reaction mechanisms like we discussed in the last video, one thing to realize is that reaction mechanisms are not necessarily known. They're proposed and then validated utilizing empirical data or experimental evidence. Now, when we look at a mechanism, it's multiple steps, multiple elementary steps, which represent basic collisions of molecules. And they can include intermediates and catalysts in addition to the reactants and the products. Also, each mechanism has a single slowest step. We call this the rate determining or rate limiting step. And every step which is faster might not be equally faster. Some might be the fastest or faster, but we just call those steps fast. So again, we're going to have a binary system of slow versus fast, even though it's not truly a binary reality. Now, when we look at mechanisms, you're going to often be presented with a mechanism and asked, is this a possible mechanism for the reaction? We need to have in our pocket a way to justify the validity of any mechanism. Remember, every mechanism must be proposed and then validated. You can't just say, well, that's the mechanism. We need to make sure we have a system in place to verify and validate. So let's talk about the 3 requirements for any mechanism to be considered valid. The first thing that we need to validate is the fact that the steps of the mechanism stoichiometrically add up to the overall reactions equation. Now, what do I mean by this? Well, it's kind of like Hess's law. In Hess's law, we had to manipulate the equations in thermochemistry in order so that the actual stoichiometry of the steps of each elementary reaction added up to the overall. That's what allowed us to add up the enthalpies or entropies or Gibbs free energies of the reactions. In this situation, we're not doing anything with the energies per se. What we're doing is we're simply making sure that if we look at all of the things on the left side of every arrow in the mechanism and all of the things on the right side of the arrow of the mechanism, we cancel out things that are on both sides, we add up things that are on the same side, the coefficients from the mechanism should exactly match the coefficients from the overall reaction. So let's take a look at this example. Now our overall reaction shows me that hydrogen plus iodine monochloride, 2 of them, react to yield 2 hydrochloric acids and 1 iodine atom, or 1 iodine molecule, should I say. Now the proposed mechanism for this is 2 steps. And if we look at these 2 steps, you'll notice that they do involve an intermediate. The intermediate in this case is going to be the hydroiodic acid, HI. You see how it's created in the first step and then used as a reactant in the second step? That's representative of an intermediate. So we cancel that out stoichiometrically. Understand this though. We are doing this only as a tool for validation. You're not actually canceling it, right? Okay, it's being used in the reaction. So it's not gone. We're just doing this as a procedure, as a process. So if we cancel out that intermediate, we add up everything on the left side of the arrows. You'll see there's 1 hydrogen and 2 ICLs. That matches our stoichiometry of reactants in the overall reaction. On the product side, you'll see that we have 2 HCl's and 1 I2. Well, that also matches the overall stoichiometry. So this reaction mechanism checks off 1 box of our 3. The stoichiometry of the mechanism, of the proposed mechanism, matches the stoichiometry of our target equation. The second requirement for any mechanism to be valid is that the steps actually make sense based off of what's reasonable in collision theory. Think about it this way. You're walking through a grocery store. The odds that you see 1 person you know, pretty good. you're probably going to run into them at least once in the aisles of the grocery store. And if you're like me, once and then say goodbye and then run into them 6 more times after you've said goodbye, because then it's just weird and awkward. Anyways, so what you're going to do is see them and run into them. Well, if you're two molecules, you're also pretty likely to run into each other. Remember, all reactions require a collision first. So two molecules which run into each other, which collide, can possibly react if they overcome the activation energy. But what if there's more than two? What are the odds that 3 friends that didn't come together all meet in the same aisle at the same time in the same grocery store? Well, that's not very common. And that's just going from 2 to 3. Now imagine 4 friends all coming separately, meeting in the same time at the same place without having made plans. Now you're talking crazy weird. So in molecules, we're looking at a very similar situation. And so in reaction mechanisms, we are going to determine validity of a mechanism by saying only unimolecular, so these are events that require one molecule, in other words, decomposition events, or bimolecular, these are events where 2 molecules collide, either 2 of the same species or 2 of different species will collide at the same time in the same place. Anything 3 or over, we consider to be unlikely and therefore unreasonable. Okay? 3 molecules colliding at the same time in the same place isn't completely out of the question. But in almost every circumstance, it's going to result in a very slow reaction rate. And so by our norms, we're going to just call that unreasonable because it's so unlikely to happen. So when I'm looking at a mechanism, I need to make sure that each step of the mechanism is either unimolecular, which means 1 reactant, or bimolecular, which means 2 reactants. And remember, when I say 2 reactants, that could be 2 of the same species or 2 of different species, or 1 of each of different species, should I say. Anything trimolecular or termolecular or above is unreasonable. So we've gone over the first 2 things. Let's look at how that example meets the second criteria, molecularity. So if we look at our second example, the first step is bimolecular. Hydrogen plus ICl, that's 1 molecule of each colliding, that's bimolecular. Reasonable. The second step, HI plus ICl colliding, well, that's also bimolecular. So that's also reasonable. We only look at the reactants because those are the only things that are going to be colliding in these mechanisms. So in this case, we would look at this mechanism and say both steps are bimolecular, therefore it's reasonable based off of molecularity. Checks the second box. The third box is more complicated, and in fact what we're going to do is we're going to spend the next 2 videos looking at how to check that third box. But what I want you to understand about that third box is this. The third necessity for a mechanism to be considered valid is that it has to have the same rate law as the experimental rate law. So in other words, we use a mechanism to determine the rate law predicted, and then we compare that predicted rate law to an experimental rate law. Like I said, the next 2 videos are going to be focused entirely off of that process. So these are the 3 boxes we have to check to determine if a mechanism is valid. And to respond to a question asking if a mechanism is valid, you must use all 3. So we have to say, does the reaction mechanism stoichiometrically equal the overall equation? If so, check. Does each step of the mechanism make sense based off of molecularity? In other words, is it unimolecular or bimolecular? If it is, check. And third, does the rate law of the proposed mechanism match the experimental rate law? So the rate law that we see in the data as the reaction is run. If so, check. All 3 meet. We can say that this is a valid mechanism. Now, be careful. Valid does not mean it is the mechanism. There could be many mechanisms. There could be a lot of different mechanisms. Some of the ways that we determine more valid mechanisms or not are going to be based off of other things. For instance, if we predict that there's going to be an intermediate, we can look for that intermediate during the course of the reaction. If that intermediate shows up, then we have some additional evidence that that mechanism could be valid. But if that intermediate doesn't show up, well, then it might not be the mechanism which is actually happening. It might be valid, but it might not actually be the true mechanism. So we are never going to make the statement, it is the mechanism. We will make the statement, it is a valid mechanism. So that wraps up today's video. We talked about mechanisms and determining their validity. In the next 2 videos, we're going to look at how to check off that box number 3. How to figure out if the rate law for a mechanism matches the experimental rate law. So I hope you enjoyed this video, and I'll see you in the next one.